So originally this talk was titled Wrangling the Internet of Things with Haskell. And after talking to some people, I got the impression that there were quite a few people who were surprised that we were even running Haskell in production, let alone sort of betting our business on it and talking about the specific way that we were using Haskell in our vertical maybe wasn't the best approach. So this talk is kind of a step back and showing some lessons and techniques that we're using to run Haskell in production in a more generic way so that you can take a step back and see whether Haskell is right for you and see that a lot of the production concerns typically associated with running a backend or a web application are solved by Haskell now. So this talk, Production Haskell, is going to be about the state of the art today. How many of you have used Haskell in the past and were kind of scared off by the quality or the immaturity of the tooling? Things like Cabal, for example. So now the tooling required for running Haskell in production has actually improved a lot, and I want to show you some of the state of the art. Specifically, everything is going to be through the lens of how we're using it at a company called Helium. So this is by no means the only way to do these things. But it shows a relatively simple example of things like building code, deploying, testing, and developing new Haskell code. So this is through the lens of how we've been running Haskell for a lot of our backend code at a company called Helium. We've been running it in production for about 12 months, and it's been working really well, so I wanted to come out here and share that with all of you. A bit of anecdotal experience to start the talk with. Of all of the projects I've worked on, our Haskell code base has had the lowest defect rate with the same amount of effort of any project I've worked on. This is obviously just an anecdotal piece of evidence, but it's been really encouraging for me to see that with the same amount of effort, we're able to focus on new features rather than worrying about breaking existing things. It's also been the easiest to refactor of any language I've used. Haskell typically has this reputation that you sort of think about a problem, go off, lock yourself in a room for a month, and then sort of come up with this perfect solution that you never have to change. And we don't really subscribe to that idea at all. We change our Haskell code all the time. We're not afraid to come up with a simple, direct solution that gets us to market really quickly and rely on the type system to allow us to safely refactor and change our code over time. This has been, I think, the single biggest surprise and thing I've been the most excited about is how easy it is to change and evolve our Haskell code base. It's been really enjoyable as well. So going to work and writing Haskell is a ton of fun. I feel like I'm sort of working with the type system rather than fighting it or wishing that I had something to help me with common defects. And somewhat surprisingly, we found quality open source libraries for just about everything we've needed to do for typical web application development, deployment, and backend development. So if you've looked at Haskell in the past and it's been a while, you should take a look again and see that the quality of open source libraries and tooling has really improved a lot in the past 3 to 5 years. Specifically, we're talking about this through my perspective on this project, which is about 20,000 lines of Haskell code we have in production. There's about 5 of us who are working on our set of applications at any given time. And we've got about 6 different services that we're running in production. About 14 months ago, we started working on a web application that was our first Haskell code that we put into production. And that was really successful, got the team excited, and so we've been building up more and more of our services in Haskell, and it's been working out really well. So specifically, we're going to look at building code, so the process necessary to get source code into some executable artifact. We'll look at deploying it, so how do we get this Haskell code onto our development, staging, and production servers so that users and QA people can actually take a look at it. How do we monitor this? So it turns out that our monitoring story is very similar to what you might expect from other languages, making sure that we're not using too many resources or that some user-defined metrics that we've created are within some certain bound. We'll look at testing Haskell code. As some of you won't be surprised to hear, testing is really fun and powerful in Haskell. And then we'll look at how Haskell can change the way we look at solving problems and common problems that face web application developers that you might sort of figure there's no solution to often have really simple type-safe solutions in Haskell. So first up, building code. How many of you experienced or heard of the term Cabal hell before? Yeah, so a lot of people have experienced this. Cabal is or at least was the most popular build tool in Haskell, and it has a lot of issues. And typically these issues arise from things like having packages have to be recompiled all the time, or slow compile times, not being able to get a set of dependencies that all compile cleanly together. And so for us in the past 5 months, we've had no Cabal hell whatsoever. That's because we're using a new open source build tool that for us has completely replaced Cabal called Stack. So if you haven't taken a look at Haskell since Stack's come out, highly recommend taking a look at it. It solved basically all of our build issues in 24 hours after we switched to it. So this has been a huge boon for us. So this is an example of converting an existing project that was using Cabal before to Stack. So we still have a Cabal file here which declaratively describes our project, the dependencies, how it should be built. And so we're going to type stack init, which is going to create a new stack.yaml file, which describes how Stack is going to build this project. Typically, this just builds on the Cabal file, so we're not duplicating any information. Then after that, we're going to type stack build, and then this will quickly build our project. And in our experience, our build times using Stack compared to Cabal are much better. Part of the way that Stack achieves this is that there's actually 3 layers of packages, the first 2 of which are completely immutable. So we have our GHC packages that are specific to a version of GHC. These are libraries that ship with GHC and are version specific. So we'll have a directory for GHC 7.8, a directory for GHC 7.10, and these are going to be completely immutable and can be shared across all projects on a particular machine. Then we have a snapshot directory, and this is for libraries that are versioned together. So Stack allows you to opt into this set of curated packages called Stackage. There's about 1,300 packages that are sort of versioned as a single atomic unit, and they're all known to build and pass tests together. And as it might happen, these are 1,300 of the most popular Haskell libraries. So with a single version number, you can get all of those libraries all building together, and you still only have to depend on the ones that are in your Cabal file, but all of these get shared across your projects. So in a safe way, you can reuse these build artifacts across all of your projects and not have to worry about one project affecting another. Then there's another layer, which is your project-specific dependencies. So you might rely on a particular version of the snapshot, but if there are specific newer or older versions of some of those libraries, then you can still depend on them in your project-specific directory, and you can also depend on private repositories that are in GitHub or RRD in your project. And so this has been huge for us because it's allowed us to spread our project into a lot of smaller projects and not have to worry about compile times from having to recompile the same dependencies over and over again. So in this example, I'm going to show changing a snapshot version from 2.22 to 3.15. And this is actually going to not just change the version of all of the snapshot dependencies, but also change the version of the compiler from GHC 7.8 to 7.10. So we no longer have to manually make sure that the correct version of GHC is in our path. All we have to do is declaratively change the snapshot version that we want, and then Stack is going to automatically use the appropriate version of GHC. And since we've already built the 3.15 snapshot from another project, the compile time to completely changing 1,300 of our dependencies that we have available using a new version of the compiler only takes 5 or 6 seconds. Now I'm going to show you an example of how we're able to also iteratively develop code, recompile the code, and interpret it for a large project really quickly. So here's an example of a little web app that previously said hello world, and without having to do anything, this tool that we're using is automatically looking at our source code, noticing when we've made changes, reinterpreting it, so it's actually using GHCI, which is a REPL that's used to interpret code instead of compiling it down to machine code. So this allows us to recompile lots of code iteratively and see the result, have our web application automatically reload all really quickly. So this has been huge for avoiding those really slow edit, build, investigate cycles that might have taken 3 or 4 minutes before. That's down to 1 or 2 seconds, which is huge for productivity. This gets us closer to a language like Ruby, where developers have been used to this for a long time. That demo uses a library that I created called Ordeal, which is just a simple wrapper around GHCI, which allows you to efficiently load interpreted code and only re-type check the parts of your project that have changed, and monitor source code to see when it's changed and automatically reload your web app or whatever it is your project is. When we run stack build, we get a self-contained executable, which is really nice for deployment because it means that we don't have to worry about having any Haskell build infrastructure on the machines that are actually going to run our production environment. So we'll look at deploying now. So imagine we have an application that looks something like this. We've already compiled our code, which has given us a self-contained binary called app. So this is going to represent our web server or something like that. We have some assets, a favicon, some JavaScript, a style sheet. And all we have to do is create a tarball, which has all this information in it. Let's say that we're going to name this tarball after a short git SHA. And then on the machines that we want to deploy to, we're going to download this tarball, untar it, symlink this particular version of the application into current, which is just a pointer that represents the current version of the app we're running in production, and then we restart the app. And since we don't actually mutate anything that was on the file system, other than changing a symlink, if there's a problem with this and we need to roll back, rolling back only takes a second. We just take the previous version of the app that was running, symlink it to current, and then restart the app again. So this allows us to easily deploy code on machines that are not required to have any Haskell build infrastructure. And when we do deployments, we can quickly roll things back if it turns out that there's a problem. We don't have to worry about a deployment mutating existing code, since we always leave the old version of the code on the machine. In production, under moderate load, we've seen our web apps use about 60 megabytes of RAM, which has been pretty great for us. Haskell has also been great for multi-core scalability. So when you're running a web application, each user's request is going to be in a single Haskell thread. Since Haskell has green threads, it's no big deal to have tens or hundreds of thousands of these threads, and then the runtime is going to distribute them evenly across all of the cores available on your machine. If you want to do data parallelism, Haskell also has really great facilities for doing things like searching a tree in parallel. So this has allowed us to take advantage of all of the cores that we have available on our machines. Next, we're going to look at monitoring. So we've built and deployed these systems. Now we want to make sure that both the Haskell runtime and whatever metrics that we've created are behaving as we expect. And the story here looks really similar to how it looks in other languages. So there's an open source tool called EKG, which is similar to CodaHail's metrics library, if any of you have used Java before. And so EKG is going to run a separate internal-only web server that allows you to get a visual representation of runtime statistics and also allows you to hook up your own gauges and statistics that represent your domain and expose them to you in a live web app like this. There's also a machine-readable JSON API. So what we've done is we've hooked up all of these metrics to Sarconis, which is the hosting monitoring solution that we use. And so we're able to get alerts if the Haskell process uses more CPU or RAM than we expect. If it's using less, then maybe that means that we're not receiving traffic. So this really looks the same as it would in just about any other language. We expose some JSON API that allows our monitoring tools to get at the statistics that we're interested in. For logging, this is very similar to other languages as well. It's trivial to log to standard out, to a file, or to syslog. So we have all of the capabilities that you'd expect to log timestamps, log source location, log stack traces on exceptions. So this allows us to quickly get at log information when there's a problem in production. Testing code is actually a lot of fun in Haskell. How many of you have heard of or used QuickCheck before? All right, so QuickCheck is a property-based testing library, and it's actually the first one. So QuickCheck in Haskell is the origin of property-based testing. And it allows you to, instead of writing individual unit tests, to talk about properties of your code that should hold true for all input. So imagine that we're trying to sort or reverse a list, and we want to test this. Instead of having to write 10 examples, or if we're lazy, 1 or 2, then we can write properties that should hold true for all input to our function. So something like the reverse or the sort function are going to take a list as input and output a list. So we can write properties that should hold true for any input list. We don't have to specify or hard code some input like we would in a traditional unit testing way. And then QuickCheck is going to generate random lists. So the empty list, a list with 1 element, a list with 100 elements, a list with duplicate elements, a list with only unique elements. And it's going to come up with all of these counterexamples that we're typically too lazy or don't have the time to think about, or we're sort of biased by our human brain to forget to include negative numbers in the list. It's going to do this for us. It's going to run however many examples we've asked for. And if that property that we've talked about fails, so a property might be something like sorting the list should preserve the count. Or if we sort the list, we can actually just brute force the correctness of that and ensure that each element is less than or equal to the next element. Same with reversing a list. If we reverse the list twice, that should be equal to the original list. Or that's also something that we can brute force, testing that the first elements now become the last, the second elements now become the second to last. So now I'm going to show you using this in a bit more of a real-world example. So let's say that we have some event type, which is a data structure that represents events that occur in our system. And this is something that we've created. And so we're going to write a property that says for all events, encoding that event in JSON and then decoding it should be the same as the initial event. So we've written some code that turns our event into JSON, and we've written some code that reads JSON and spits back an event if the event is valid. So all we have to do to write this test is write a function that takes events, because we don't care what the specific event is. This property should hold true for all events. And then it returns a Boolean, true if the test passes and false if it doesn't. And the first time I ran this, it turned out that this property failed. And the error ends up being here. We have some sampled value, which is going to be a key in our JSON that has a timestamp. And so if we look at this particular timestamp, we see that it's down to the microsecond resolution. And if we encode this into JSON, we actually lose a decimal place here. So when we read this back, we've actually lost some precision. So this is just some small subcomponent of our larger event. And this is the kind of bug that, had we written manual tests for encoding and decoding this large thing, it's very unlikely that we would have come up with this example. So even for relatively high-level tests, we're able to find bugs that are really subtle in subcomponents of our data structures. And so this might let us know that the particular library that we're using to encode dates into JSON only supports at the millisecond resolution, or that maybe there's part of the JSON standard that we've misrepresented or misunderstood. So this allows us with really minimal effort. I mean, we saw the test here is literally 1 line of code, and we can sit here, run this overnight, run 1 billion examples of this, and find really interesting subtle bugs. Next, we're going to look at how we can use Haskell and the type system to solve interesting problems in a concise and elegant way. The example here is actually encapsulated in an open source library that we have called PostgreSQL Transactional, which is available on our GitHub page, so you can check that out afterward. And the problem we want to solve is that we want to be able to write reusable queries and database statements that we can compose together. And as we compose those, we want to be able to talk about how the composition of these should be used within a transaction. And then that should become a new component that we can reuse. And it turns out that the naive way of solving this actually has a really interesting problem with transactions in typical relational databases like MySQL and Postgres. So let's look at a really simple example first. We're going to write a function called lookup_user, which is intended to be a reusable query that new parts of our application can reuse and can be composed into larger queries. So lookup_user is going to take an email address, and then it's going to call this query first function, which is going to execute the query and return the first result. It's going to pass in the email address to be substituted, and then we've got some inline SQL code, which is going to select the appropriate columns from the user account table, and then have a where statement on the email address. So we're only going to look up users with the email address that we've passed in. And so let's say that over time, we start collecting these reusable queries. All is well and good. Then we want to create a new reusable component that's going to call all three of these inside of a transaction. So cuz is going to be the composition of foo, bar, and baz, and its correctness depends on foo, bar, and baz all being run inside of a single transaction. So this is great, everything is good. Then later we implement a function called buzz, and things are still okay. Now we want to create a larger query, which is going to first call cuz inside of a transaction, and then inside of that same transaction call buzz. So fizz should be a larger transaction that calls foo, bar, baz, buzz, all inside of a single transaction. And this whole thing, its correctness is dependent on atomically executing all four of these statements. So we want to make sure that if any of these fail, the whole thing rolls back, or if it succeeds, the whole thing succeeds. And it turns out that there's actually a serious problem with representing the problem this way. And that's that relational databases like MySQL and Postgres don't support nested transactions like we've generated. So what happens if we sort of encode this the naive way is that we generate 2 begin statements and then 2 commit statements. So the database is going to see the first begin statement, which corresponds with the beginning of that outer transaction. Then it's going to see a begin statement, which corresponds with starting the inner transaction. The database is going to say, I'm already running a transaction, so I'm just going to ignore this other begin statement. Then it sees the commit statement from the inner transaction. It says, hey, I'm running a transaction. I'm going to commit that transaction. So now we've created a transaction that was begun in the outer transaction and ended in the inner transaction. And then we get the commit statement from the outer transaction, and the database says, oh, I'm not running a transaction. There's nothing I can commit. And if you do this, you actually get a warning back from the database. So that first begin statement that was ignored, it says, hey, there's already a transaction in progress. I'm going to ignore this begin. And then when we commit at the end, we ignore that. So what happens is we actually end up creating a transaction that starts at the begin of the outer transaction and ends at the commit of the inner transaction, which means that this is going to commit, and then if there's an error, buzz might not be executed or might be executed not atomically with the rest of this. So it turns out that this sort of naive formulation where each component talks about transactions on its own doesn't actually have the semantics we want. And if we're not careful, we can accidentally write code that does this and has really interesting and hard to find failure cases. So we have 2 choices here. We can either not wrap cuz inside of a transaction and sort of say that, hey, I really wish I could wrap this in a transaction, but in order for you to be able to reuse it, I shouldn't call it in a transaction. And so we just have to put a comment and sort of rely on social convention to make sure that this is wrapped inside of a transaction. Or we can say that cuz is this transaction that sort of must be executed on its own, and I'm sorry, but it's not a reusable component. And if we look at the types of this, it starts to become clear what the problem is. So we add a type signature to our lookup user function. We're going to take some connection, which represents a connection object to the Postgres or MySQL database, a text value representing the email. Then we're going to return some IO action that optionally returns a user if a user was found with that email address in the database. Then we start creating some more of these. So we have a function to create an organization, which is going to take a connection and some organization, and then maybe a function to add a user to a particular organization. Then when we compose these together, we wrap this in a transaction. So this is our sort of reusable query that is made up of subqueries. We're explicitly wrapping this in a transaction. The other option that we have is to sort of put this comment and say, you must wrap this in a transaction because the correctness of this component is dependent on executing these 3 statements inside of a transaction. So this is sort of the Haskell code example of relying on social convention to do this. Then when we reuse this somewhere else, we wrap this whole thing inside of a transaction and we say, first create the user and organization, then do something else, and we're going to wrap this in a transaction. So it turns out that there's a really simple way that we can use types to completely avoid this problem while also allowing us to reuse these components and make sure that they're always run in exactly one transaction. And the solution is to change the type of each of these queries. So before we took in a connection object, some text value which represented the emails, and then we immediately return some IO action to be executed, which is going to, in a side-effecting way, go out and query the database. And so it turns out since we have a lot of functions that take in this connection object, we can just elide that entirely. And then instead of returning an IO action, we're going to create some new type called PG transaction that doesn't actually execute IO. It's just the composition of some queries. And so we can return this PG transaction value. And then the only way that we give ourselves to turn a PG transaction value into an IO action is through this one function. So if you have some PG transaction, just having it doesn't actually do anything. That's not going to execute any IO. And so the only way that we export to turn a PG transaction value into an IO action is through this run PG transaction function, which is going to always wrap the composed PG transaction value in exactly one transaction. So we've used types to make sure that we can compose these queries up, make sure that as we compose them, they'll always be run in one transaction. So our code actually looks a lot simpler now. We don't have to talk about this connection anymore. We don't have to talk about transactions as we compose things because implicitly when we compose things together to create a new PG transaction value, we're always going to be inside of a transaction. If we want to do things in 2 transactions, we have to compose something, call run PG transaction, compose another PG transaction value again, and then call run PG transaction there. So if we want things to be in separate transactions, we have to be explicit about it. So here, our create user and organization function becomes a little bit simpler. We don't have to talk about wrapping this in a transaction. We can safely reuse this set of queries inside of foo, compose that with something else, which is going to do another action, and then call run PG transaction on this larger composed set of queries and make sure that this entire set of database queries and statements are done in exactly one transaction. Something else comes out of this, which is that if we want, we can prevent ourselves from doing long-running IO actions inside of a transaction. So when you make a transaction against a relational database like Postgres or MySQL, that takes up resources on the database side. And so typically speaking, you want to keep your transactions as short as possible. You don't want to do things like make some HTTP request inside of a transaction or sleep for 5 minutes accidentally. And so if we try and compose a PG transaction value with something that is some slow side-effecting thing, this actually just fails to type check because Not allowed is expected to be a PG transaction value, and so we can't compose our create user statement with this slow side effecting thing. So if we want to prevent ourselves from accidentally putting some slow side effecting code inside of a transaction that we're intending to keep short, we can actually lean on the type system to make sure that we're not accidentally doing side effecting things inside of a transaction. If we want to allow ourselves to do that, then we can change the types slightly to allow ourselves to do this. But we're given the choice, and we can actually choose whether we want to be a little bit more expressive in this particular case, or if we want to be a little bit safer. So that was PostgreSQL transactional. This is available as an open source library. The whole sort of core of the implementation of this is like 5 lines of code, but it's a fun example to throw up on GitHub. So this is available on our GitHub page. So we've now seen how we can build Haskell code into an executable, statically compiled binary from source code. We've seen that modern Haskell tooling like Stack solves a lot of the problems that we previously had with build tools like Cabal. We can, in a declarative way, talk about the specific version of the compiler we want. We don't have to muck with the path or deal with dependency resolution hell. It's easy to deploy our code since we're just producing statically compiled binaries like you would with C or Go. All we have to do is unpack a tarball and then run the executable on some machine with the same architecture. We don't even have to have the Haskell compiler or anything like that on the machines that we're going to run. So you could actually distribute an executable to all of your users and not have to worry about them having anything related to Haskell installed. Monitoring Haskell code is much the same as with other languages. We have a tool called EKG, which is an open source tool that allows us to get introspection, both human readable and via a JSON API, into the Haskell runtime and to whatever custom metrics we want. Testing is also fun and easy with Quick Check, which allows us to quickly write powerful tests that can be run for as long as we have the CPU time and the patience to run. We don't have to worry about manually coming up with unit tests that we want to test and specific examples where we're sort of left to our own imagination to make sure that we remember to test with the empty list and -1 or some particular Unicode character. And then we've seen how we can use the type system to take a simple problem that web application developers may face, whether they know it or not, and encode a solution in a simple and type-safe way that allows us to continue to compose queries the way we were before, while also having the transactional safety and semantics that we intend. So thank you. All of the open source libraries I talked about here are on our GitHub page. The slides for this are on the link below, and I think YOW is also going to be posting those up soon. And I'll be happy to answer any questions. Thank you.